Engineers love automation, and Wealthfront automates your investing. As a software engineer, there are certain processes that you want to execute no matter what, like integration tests during a build. You wouldn't execute integration tests manually. You would use a continuous integration tool like CodeShip or Jenkins to automate your integration tests. Wealthfront is a tool to automate investing. Just like a continuous integration tool runs your tests automatically, Wealthfront can reinvest your dividends automatically and perform tax loss harvesting automatically. To get your first $15,000 managed by Wealthfront for free, go to wealthfront.com/sedaily and get started with Wealthfront's layer of automation on top of your portfolio. Wealthfront.com/sedaily. Check it out. It would support Software Engineering Daily, and you will get $15,000 managed for free if you sign up. Automate your investing. Get back to the things that you can't automate, like writing code. Josh Bloom is a professor of astronomy at UC Berkeley and is also the CTO and co-founder of Wise.io, a company that is building machine learning products. Josh, welcome to Software Engineering Daily.
Thanks for having me.
What is a machine learning system?
Well, the way I think about machine learning systems is one that lives in a production environment and is supplying something that machine learning does, which is namely making predictions that have some value. And in the case of what we do, it has some business value to our clients. In the case of scientific workflows, there are pieces of machine learning applications that are looking at data and essentially helping scientists do better with that data, from discovery to inference. So the way we think about it is not so much what you might think of machine learning at the academic level, where you're writing papers and showing, my scaling curve is better than your scaling curve, but something that's actually showing real value to sort of end users.
So you do see a tight mapping between machine learning systems and predictions.
Yeah, absolutely. And in some sense, maybe I'm limiting myself too much to talking about those in production where you have a system that's interacting with the world. Those are the ones that I've spent most of my time building at Wise, and the ones that I was doing working at UC Berkeley in the scientific case. There are plenty of other machine learning systems that could act in more of a static way, giving high-level insights. So you can imagine what's called unsupervised learning, where you take a lot of data and you answer questions with interesting machine learning tools that even people haven't thought to ask. So finding, clusters in a high-dimensional space, for instance, may give you some interesting insights of where to put more of your resources. Or if you're doing drug discovery, there may be some really interesting facets of the data that you didn't realize clustered together, and that may be an interesting avenue for further pursuit. So there's certainly realms where machine learning is useful for giving insights, in a one-off kind of way, or in a sort of slow way, where people are the ultimate consumers of it. The kinds of things that I think about when I think about machine learning in production are ones where you've got data flowing in, you've got answers that are required in a short time scale, not necessarily real time, but for instance, if you've got a type of application where you need to make, say, microloans in a peer-to-peer sense. I'm sort of making up a company here on the fly. You wouldn't want to have thousands and thousands of analysts looking at all of that data and trying to make decisions in a few seconds. But you might want to have machine learning opining on whether this is a good loan or not, or what perhaps the cost of the loan would be, given the different risk factors, and then push that along. Ultimately, in the end, you're going to wind up having people be on the receiving end of those predictions, but it may be sort of deeper into the stack than they know about.
Okay. And so much of the talks that I've seen you give deal with this idea of putting machine learning systems into the wild, into production. And I saw one talk you gave called A Systems View of Machine Learning. And one of the first topics that you discussed was this paper that came out of Google called Machine Learning, the High Interest Credit Card of Technical Debt. And we had Dee Scully on the show to talk about that paper. It was a really interesting conversation. Why did that paper resonate with you?
Well, I think and I listened to your podcast with Dee Scully, which I thought was fantastic. I think that's an important paper, as he said, not because that Google team discovered something novel about how different machine learning in production actually is from normal software engineering. And in fact, Leon Bateau at Facebook has been talking a lot about the erosion of the abstraction boundaries that you typically like to build up when you build software stacks that comes with machine learning. But as Dee Scully said, it was because they were the ones that took the time to actually write it down. And when they go and they give talks, there's a lot of head shaking because they wind up putting to words the kinds of things that practitioners feel all the time, that there is something different about machine learning. And the way that he describes it well in that paper is that data winds up sort of carrying with it these boundary abstraction erosion techniques, right? So you wind up intermingling parts of your stack in ways that you never thought you could, even though you have very specific, say, APIs of how these things should talk to each other. And so the reason why I bring that up when I give talks is because I often will wind up talking to a largely academic environment or an environment where you've got software engineers who are sort of interested in machine learning and think what they need to do is just bring in another module and then that will solve their problem. It's particularly important for those people to understand that this is a different kind of beast. And so I like to talk about the Dee Scully paper as, I think, one of the canons of data science literature. And it hasn't, I think, arrived to that point yet, but it is such an important paper for people to understand. I also use it in my own company in helping us when we're selling our product with our clients or potential clients in understanding just how hard it is to do themselves. So we use that paper as a selling tool in some sense around the build-buy decision, which you wind up finding a lot now. You've got very sophisticated companies who are now getting sort of deep DNA around data curation and making use of data for their core business. And when they start thinking about bringing deep analytics or machine learning out to various aspects of their business that perhaps isn't their core, say in their HR department or customer support, the nominal assumption is that I can just bring in a couple data scientists, they can solve this problem, and then we're done. But as that paper says, and I'm not going to get the quote exactly right, it may come as some surprise to academics to know that machine learning codes in production are at most 5%, machine learning and machine learning algorithms, and at least 95% glue code. So it's a massive gulf from going from something that looks wonderful on paper, where you've got a beautiful result and you say, my accuracy is going to be this if we could only put this into the wild, and then actually putting it into the wild and all the bugaboos that come with that.
So perhaps the world agnostic of this paper is the mistaken idea that we could just sprinkle machine learning onto our pre-existing system and it's cleanly partitioned and it will just give us a more robust, more delightful experience, when in fact the reality is that machine learning introduces some maybe not tight couplings, but certainly integration points that will affect the business logic of your software. Would you say that's accurate?
Yeah, I think that's a great way to put it.
Okay, interesting. So I'd like to get your idea of a generalized architecture for a machine learning system. What are the different components that compose a machine learning system?
Well, it obviously all starts and ends with the data. If you're starting to talk about the software stack, there has to be an ETL component that is interacting with the outside world. So if you think of your final machine learning system in terms of endpoints in some larger software, and services oriented architecture, you have a number of endpoints where the data is flowing in, and perhaps metadata about that data is also flowing in through different endpoints. And on the other side of that, you want predictions that are going to be consumed in other parts of the large software project, and those can also be expressed as endpoints. So if we define a machine learning system as that, you're already putting these boundaries on what essentially looks like a black box. So that there's lots of exciting things of being able to look inside of that black box and tweak it. Getting back to the Scully paper, I guess the argument is that there is no such thing as just RESTful endpoints where all the data happens upstream, and that's not really part of the system, and all the predictions come on the back end of that, and that's not really part of the system either. The whole point is that the system is the full end-to-end. But if we're sort of allowing ourselves from a software perspective to think about where we would put those boundaries, you can imagine having a machine learning system or a large fraction of that machine learning system be those ones defined by those endpoints. So the question then is, what's inside of that? So inside of that is the thing that's going to wind up consuming that data, making sense of how we take this stream of data, normalizing it into a schema that can then be featureized. And by featureized, this is where you wind up pulling signals out of that data with code. So in the case of audio data, for instance, you might be running fast Fourier transforms on that and pulling out dominant frequencies. In the case of text-based data, you might be doing some natural language processing and pulling out important words. And there's a whole bunch of interesting work along all the different facets of feature engineering. On the other side of that, because most machine learning models require essentially what you might call rectangularized data, you've got rows and columns, rows being different instances of your training examples and columns being the different dimensions of the featureized data. You are essentially building a model that outputs what the final labels are in the case of supervised learning. In the case of unsupervised learning, you're then basically just taking those rows and columns and trying to make sense of how these instances are related to each other. You build those models. You obviously have to have a sense of what all the different hyperparameters are of the model and the featureization, and in some sense, some hypervisor, which is during the full creation process, making sure that you're using the optimal models to get an optimal answer. And then in some sense, you're done. You have a model that correctly or most accurately outputs new predictions on old data. And then the way to think about it is you then want to take that model and the whole featureization pipeline that you've created, apply it to new data as it winds up coming in, and then spitting that back out of the back end. So each one of those pieces, in some sense, can be modularized and containerized. And in fact, what we do at Wise is express these different pieces inside of Docker containers and make sure that the sort of core IP of what we've built that allows us to do this stuff very efficient and both from a memory perspective and time perspective is expressed in a high-level language that allows our data science team to be able to create these workflows effectively as a glorified config file or JSON file, and then orchestrating all that together inside of a large scalable infrastructure like AWS is really what most of the engineering effort is here.
Okay, so we will get into those implementation details. Those are definitely really interesting. But speaking at a higher level, just about newer software packages. I mean, you mentioned Docker, but I was thinking, some of the things that you've mentioned in talks that you've given, software packages like Spark and Theano and scikit-learn. These are software instantiations of algorithms that get used in practice. And these software packages make it much easier to do things like k-nearest neighbor or decision forests or even deep learning. What is the broader impact of this improved ease of use that we have with machine learning algorithms?
So you can talk about it both in a positive way and a negative way. And the negative is more about just sort of these beautiful nooses that we've created that allow people to hang themselves. the way I think about it in a positive way, it means quicker time to value for a data science team building a new machine learning project in production. So, if you're in a data science team and it comes down from on high that we need to add machine learning to this various aspect of our product, you're going to think about how you would wind up constructing that workflow. You may already have existing infrastructures like we built proprietary ones at Wise, and you just sort of plug into that. But if you're starting from scratch, unlike what it would have taken 5 years ago or so, you can now get up and running with a very interesting and useful solution, or essentially a prototype, in a very short amount of time, just because you're not having to do all the software carpentry for the actual model creation. Some of the most interesting packages, I think, are the ones that are going upstream from just, say, allowing you to do lots of different types of deep learning, to ones that are allowing you to do featurization in a parallel and memory efficient way. So, for instance, GraphLab Dado is an interesting software package that isn't just focused on algorithms in the Python ecosystem, I should say, but is also giving a lot of thought to how you take, say, a corpus of text and featureize that very quickly. Spark, for instance, also has some plugins that's allowing you to do that featurization very efficiently as well. Most data scientists, when you sit them down and ask where they spend most of their time, will wind up having those few algorithms and software packages that they really like for the learning part of it, but most of the original thought, most of the hard stuff is in the feature engineering. And so that's an absolutely wonderful place that we've arrived at, that we've got different pieces of that software stack that are the instantiations of those algorithms that have, wonderful provable properties on paper. The problem is, again, it comes back to that systems view. If you're building a model, say using, let's say TensorFlow, for instance, and you really don't have much experience with the domain. So you're trying to build something that's, let's say, give some insight into videos as the data streaming in. You're going to wind up spending a lot of your time on the ETL part of where does this data come from? What happens if there's a frame that drops out? There's all the things that have nothing to do with machine learning itself, but just with the data engineering and the data provenance. So a lot of time will wind up being spent on that. But of course, again, 5 years ago, if you were going to build some cutting edge, deep learning network, you'd be coding all this stuff from scratch, and you'd have to learn CUDA to work on GPUs. And now you just don't have to do any of that anymore. So it becomes turnkey. In some sense, from all software is just killing bottlenecks. It just removes a huge amount of bottleneck around the whole model building.
Sure. Okay. So removes the bottleneck around the model building, and then perhaps shifts the bottleneck to the production. Would you say what are the challenges to putting a machine learning system into production?
So the first part is getting, which I think is the bread and butter of well-trained data scientists, and I'll use air quotes here because I have thoughts on what a data scientist is and isn't. We can maybe talk about that later. But getting to that first step of showing on paper that from historical data, the model that you've built and essentially the entire workflow that you built would be useful for the question that's been asked. And that's an important thing that oftentimes we don't discuss because it seems so obvious for practitioners, is that doing good machine learning in production means that you've articulated well what the question is that you're asking, or a related one, which is what is the business value of the answer. And until you've articulated that question, everything you're doing is just exploration. So if you're presented with a large corpus of data, and your boss says, find something interesting that may be of value, that's a very different pathway than I need machine learning to, let's say, improve this widget right here. And I need to know whether that thing should be red or blue, and do everything you can to get me that point, because I've articulated upstream from you what the real value of doing that right is. So there's a huge amount of exploratory work that could go into something which eventually could wind up going into production if it's determined that that's important enough. But when you've already decided this is the path I need to take, or this is the answer I need to get to, because I know I need to put in production, obviously the first step is to show on paper, in retrospect, that with the data that we already have in hand, things could be really useful for us. So that's step one, and then of course there's all the soft aspects of then getting the buy-in to then go to the next step of actually putting it in production. Typically, when you talk about putting machine learning in production for an established business, you're talking about replacing existing systems, or if you're doing it well, I think you wind up living alongside existing workflows. And there you have to understand, how do you have basically two inputs to this problem, one coming from potentially people or business rules or the status quo of how this workflow has been done in the past, and then this newfangled way of getting a machine learning answer. So to be specific, going back to the original business problem we set up around microloans, you can imagine that you've actually had people, in some foreign country helping you make those real-time decisions about whether you issue this loan. Now somebody says, well, let's try this great thing that looks awesome on paper of us being able to get slightly higher ROI out of, putting machine learning into this system. Now maybe you try to have to architect something like 10% of all the decisions being done by the machine. You run effectively an A/B test between humans and people. You wind up realizing that the humans are doing not as well as people in the long run, because it takes a while for there to be a default. So you have to be measuring, essentially who's winning. And then over time, you might creep up all of the predictions coming from the machine. So that means you have to put what you've just built in a workflow sense into an environment that's already been running, and there's obviously big pains around that. You have to be able to monitor and measure how well it's doing, and make sure that you've got some fail safes, so that if the machine goes wild and gives everybody a loan for zero interest, you're not going to allow that to happen. So there have to be these safeguards outside of that. And then you have to constantly be monitoring its quality versus all the alternatives. And then once you get to this, sort of happy place where you've now replaced the old workflow where people, experts have been opining on data, you have to be thinking very deeply about the explore exploit. One of the challenges with machine learning in production, which again, going back to the Scully paper is discussed, is that when you build a model that looks great, you put it in production, and on the first day you make 10% more money than you would have by other means. It doesn't mean the next day you're not going to lose 100%, right? Because the world is changing. The data inputs that you have are changing. And a critical part of all of this is making sure that you've built feedback loops into the system, both positive and negative feedback loops. You need to make sure that if you are making a prediction about what's going to happen in the future, that you get the final result of what actually did happen. Because if you're wrong, that data needs to be fed back into the next time that you build a model. And the best companies are continuously building models, right? So think about, say, Gmail and spam. Right, we don't even think anymore about us going through and curating our, business rules that we might have built up, like in Microsoft Outlook 15 years ago, and said, well, actually, if it has the word Viagra, but it comes from Nigeria, but it comes from my dad because he's a Nigerian Viagra salesman who just won the lottery, then do this, then do that, right? So you wind up having to continually build these models. And the best machine learning systems in production, the ones I think get us to the place where machine learning is just part of our lives, is the ones where all this stuff is just happening seamlessly under the hood, right? So you don't know when Gmail has built and updated the model for spam. You just continually wind up believing that its spam filter is better than anything that we've ever seen in the past. And so they have to have a full system for building these models, putting them in production, and likely what they're doing is rolling out new models for a small subset of the population, seeing how well those do, rolling them back when they don't do well, and having a full end-to-end system that's capable of doing that without any noticeable impact to the end user.
So the Gmail example, obviously we can't know for sure what happened in this instance, but I think you've touched on this in one of your talks about how Linus Torvalds went off on a rant about how Gmail randomly started categorizing all of his a bunch of his calendar invites and stuff as spam. And this was, I think, shortly after they had announced some breakthrough in their machine learning spam filter categorization algorithm. So, hypothetically, like, do you, when Linus blogged about that, do you think the Gmail spam team suddenly had all their hair caught on fire, or do you think it was a simple like click of a mouse, roll back the model somehow type of? I mean, how in the ideal world of a machine learning production system, what would that rollback process look like?
It's a great question. So I should say I don't know what happened behind the scenes, but I do believe he had a follow-up blog post, which ironically was on Google Plus, saying, "Yeah, things look better now with my spam filter. So thanks." So either something happened, or he was an anomaly, or they rolled back just for him, or something. Right? He's a big enough personality that he probably gets special treatment. So there's a couple things to say about that. Number one is, I like to talk about fault-tolerant machine learning, which is that in the end, if you make a mistake with your answer, so in this case, is it spam or not, it's not catastrophic. So people aren't going to lose their life, right? And yes, Linus got mad, and maybe it wasn't very good for Google stock, at the 1 penny level or something like that. But in the end, it wasn't such a big deal because the data was still there. He was obviously looking through his spam filters every now and then because he knew there were messages. It wasn't the end of the world. And another example I show is where Netflix recommended Sons of Anarchy to a 6-year-old, and there's a cool there's a cool little screenshot on Reddit. That's not the end of the world. If the kid clicks it, and watches a little stuff, he'll probably be freaked out. That's maybe the guy cancels his account, but it's not catastrophic. When you talk about what is catastrophic, you would talk about machine learning in the real world. Ultimately, it comes down to what's the loss function. And there is a cost of being wrong in both directions. There's a type 1 and type 2 error. And, you're trying to minimize the amount of false positives while also minimizing the amount of false negatives. And, Google spam filters has gotten to the point where most people feel like where you are on that, what's called the receiver operator characteristic curve or ROC curve, where you are on that for most people is fine. But somebody like Linus may never, ever want to miss a single message that could potentially be of interest to him, in which case, 0.1% false negative rate, or depending on how you look at it, maybe it's a false positive, he can't stand that at all. And so one of the challenges is that Google has is that they've got, hundreds of millions of users. Not everyone's ROC curve is the same, right? Not everyone's sense of a loss function is the same. And so, ideally you would wind up having in a multi-user system that's being served by essentially a single model or a model that's built off of individuals and leverages, more of a global model. You'd want to start learning over time what people's sense of loss is, right? So potentially Google would be looking at how many times are people looking in their spam filter and pushing things to the other side, not just to get new labels about what they got right or wrong, but how important is it for them to catch messages that, potentially could be of interest to them. I, for instance, never look through my spam filter. If there's stuff in there that's important, I'm assuming people are going to wind up emailing me by other means or text me or something. So I think that's critical is when you think about putting machine learning in production is make sure that in a sense you have these ultimate safeguards where you're not going to wind up pulling the trigger on something that could be catastrophic. If you're making predictions of that scale and of that import, you'd like to have people be the final arbiter of whether this is worth going or not, right? And so you think about AI on drones, right? And there's now a big push to try to get, for instance, the UN to ban, artificial intelligence drones, where they're basically making kill decisions on their own. There, it could be that you allow them to make the kill recommendation, and somebody just has to say yes or no as the final, safeguard on that.
Interesting. Engineers are always looking to simplify. To simplify testing and deployment, engineers turn to CodeShip. CodeShip is continuous integration and delivery as a service. With CodeShip, your tests are executed against your code automatically whenever you push to GitHub or Bitbucket. On Software Engineering Daily, we've done several shows about DevOps, and continuous deployment is key to DevOps. It's a great way to break down the wall of confusion between development and operations. Managing your own testing infrastructure is painful. That's why you want a service like CodeShip to do it for you. If you have a huge number of tests, you can use CodeShip's Parallel CI to run all your tests in parallel. CodeShip will spin up containers on their own infrastructure to run your tests in parallel. If the code passes your tests, CodeShip will deploy it automatically to your users. Companies like Product Hunt are already using CodeShip to speed up and simplify development. To sign up for free and start shipping today, go to codeship.com. Or to try out CodeShip's new Docker platform, go to codeship.com/Docker. So, okay, you mentioned the well-trained data scientist as a, I guess, point of contention. I have a number of conversations with my friend Srini Kadamati, who's been on the show, and he was talking about how, data scientists, there's kind of this bifurcation of roles between data scientists and data engineers, and then I guess there's also data analysts. I guess we can partition the behavior of the classical data scientist into these three different things, or I don't know. I'm just curious about what your views. You mentioned the well-trained data scientist. What are your views on data science and the role of the data scientist?
So the way that I've said it as succinctly as I think I can state it is that I don't believe that there are data scientists, but I believe there is such a thing as data science teams. And so that is mostly just a statement that, the analog would be there's no such thing as a full stack engineer. So this is somebody who is at best incredibly good at one part of the stack and quite knowledgeable about other parts of the stack. And so in the context of data science, if you look at the way it's been traditionally defined as the kind of union of somebody who's good at math and algorithms and computer science with another part of the Venn diagram of somebody who's good at hacking and programming. And then the other part of the Venn diagram is somebody who knows the domain problem and can interact and can explain their results to a broader audience, either their boss or their customers. And that one I think originated from Drew Conway, for instance. I look at that Venn diagram as essentially defining a null set in an individual. But when you're building up a data science team, the idea of hiring somebody who's got a PhD in stats or computer science, somebody who has, is a seasoned software engineer, and maybe somebody with an MBA who knows some computer programming, means that the three of them can get together and solve a really interesting problem. Doesn't mean that they don't have to know how the other pieces of the pie fit together. Doesn't mean that this MBA person can not know any programming at all, or this algorithms person doesn't know what the Python programming language is. They still have to be knowledgeable about other aspects of what data science is, but they don't have to be experts.
The team of T-shaped people over the singular, what is it, N-shaped person? Or?
Yeah, so I think, The idea of a pie-shaped person came from somebody named Alex Zalay. And the idea is there that you've got somebody who's incredibly deep at, say, a domain question, who's potentially written papers on, I'll take something from my own field. In astronomy, you're writing papers about some cutting-edge question in cosmology, but then you're also basically pushing the envelope in a new realm of statistics. And so that's sort of the deep two legs there. And then instead of T, I call it a gamma-shaped person, right? So it's somebody who's very deep in one of those aspects. But then if you think about the little drop down, then that person could have a lot of knowledge about what is cutting edge in statistics, if not being able to be the person to actually push that knowledge themselves. It means that when they meet somebody who's also gamma-shaped, who's very deep in stats and knows a little bit of astronomy, for instance, the two of them can get together and do something novel.
Okay. Interesting. So let's talk about Wise.io, which is your company. What are you building there?
So we're building these end-to-end applications that sit on top of SaaS-based platforms around customer success. So think of us as broadly the intelligence layer atop people-to-people interactions for business. And one of the specific things that we have out in the market is a set of applications around customer support. So in that case, we're helping our customers in efficiency and automation around how they interact with their clients. And so what we do is we wind up learning from past interactions of how a company has interacted with their clients. Say somebody sends a brief support email and says, "I need help resetting my password." They will wind up getting back typically something that feels somewhat bespoke for them, saying, "I'm so sorry you're having a hard time with your password. Why don't you go to this webpage, or here's the 3 steps you need to do to reset your password." Those are typically templatized by support teams. We're effectively making predictions for this incoming message that it can be answered with this template or with this macro. And in the cases where we have a lot of confidence, we'll just answer it. So it solves a lot of pain in the sense that you have these support teams which are growing very quickly, and they're not capable of hiring people fast enough to actually fulfill in a timely way the kinds of requests that are incoming. And so this allows support teams to scale sublinearly, which turns out to be really important for companies that are growing. Interestingly, what we've seen, and we've been told this by CEOs, is that they see the number of support tickets growing linearly with revenue. So companies that are growing and growing their revenue are having obviously more clients, which is a great thing. But even if they've figured out a way to scale all the other aspects of their business, there's still this sort of endpoint where when people touch other people, you think that you need sort of a one-to-one relationship. And in the end, what we're able to do is leverage the power of what great support agents are already doing, and basically become sort of super augmentative in their work, so they can answer many more problems in the same finite amount of time.
Okay, sure. So I totally understand the product offering, and I'm curious about the implementation side of things. So at the first level, like I think about the data ingestion layer, and I think about like all different companies that have customer service have different types of different data formats, and how does Wise.io normalize the data from different clients to be consumed? Because you have to consume them in your machine learning system in a way that is well formed by the machine learning system. So how do you normalize, or I guess maybe the term is clean, that data, like to be ingested by your machine learning systems?
So one of the decisions we made early on in the company was to work with third-party SaaS-based, essentially systems of record, so that we wouldn't have to be the data lake for where people are interacting with other people. And what's nice about that is obviously we didn't have to build that part of the stack, and we could work inside of API.
So, sorry, what's an example of a data lake like that?
Zendesk,
Okay, got it.
Salesforce, right?
Right.
So these are places where essentially their UIs on top of databases with some services around them. That's the interaction point where incoming emails from customer is then dealt with by a customer support agent. So we build on top of those systems, and the nice thing about that is there is a fairly fixed schema of how the data actually is presented to us. So we don't know what the text is or even the language that's going to be used inside of, say, an incoming support message. But we know that there's a text field, and we know there's a date time field. We know that there's a from field. We know that there's a connection in a CRM sense back to who is this person, how much is this account worth, et cetera. And so it allows us to build data science workflows against data we've never seen before because we're building it against a schema that's essentially fixed and knowable for us. So there is no data cleaning in a sense that we don't have to get a new customer as they wind up onboarding and go, oh no, they've got this other feed, and now there's all these other fields we've never seen before. We've built sort of a middleware layer, which has nothing to do with machine learning, that is capable of ingesting that. We've normalized, for instance, both how Zendesk thinks about support from their own internal schema and how Salesforce thinks about support. And then we're going on to a third system. It turns out that a ticket is a ticket, right? And a conversation is basically a conversation. And all the metadata that you have about that is something that you could wind up ingesting, rectangularizing it after you featureized it, and then building models on it. And doing all that without any people in the loop is sort of where a lot of our innovations have come.
Okay. Yeah, that's a beautiful statement of the problem to you. If it's coming to you in this well-formed format, that's in high contrast to. I did a show recently about this company, OpenGov, and they're kind of offering like you can think of it as sort of like a Quicken for governments, and so in order to ingest the government data, they have to work closely with the governments and figure out what data format it's in, and this could just be like a showstopper problem. But it sounds like by having this sort of not middleman, but you've got Salesforce or Zendesk architecting the schema for you, and you just have to abide by their contract. So it's beautiful. Okay, let's talk about implementation at a lower level. One of your goals is to have a system that simplifies and abstracts away the machine learning process so that the data scientists and the engineers don't have to spend the time onboarding clients. What are the steps to achieving this?
Well, certainly a lot of painful steps in the sense that you have to have data scientists and engineers being part of the initial onboarding of your initial customers. But where you're trying to get to is building those systems that don't require them or minimize the total amount of time that it takes to onboard. And that's how you wind up building a scalable enterprise software system. Is to not require people to be part of that onboarding process, let alone the maintenance process. So, as I said at the beginning, we've built this sort of end-to-end machine learning workflow that, in the case of endpoints, as we talk about machine learning as a black box, which I'll say right away, as we said before, not a great way to think about it, but we've allowed the data scientists to live within this black box and build out workflows and make tweaks to existing templates of, let's say, so another feature that we have isn't just making recommendations to agents of how to respond to a ticket, but we'll also automatically characterize an incoming ticket so that it can be routed to, let's say, the right agent who has the highest probability of closing it in the shortest amount of time with the highest customer satisfaction. Or just making predictions effectively of which categories these belong to so that our clients can use that data to do reporting and things like that, and which is required internally. So, we think of that as essentially a multi-class classification problem that data scientists have at their fingertips because they built it and our engineering team has built it. A number of different modules that they can use to attack, let's say, incoming Zendesk data, make all the features they need, and spit out those predictions, which are then consumed by our API middleware from what we call the Wise Factory, which are the ones who are responsible for making those predictions. But when the data science team is building this for the first time, they're basically just building this on their laptop, and they've got static data sets of essentially historical data dumps from, say, company X, Y, and Z, and they're making sure that they're getting out good answers because you can do all the normal tricks of holding out some of the data and making predictions on that where you know the answers. You get your expected levels of accuracy. So they can wind up basically gaining a lot of confidence in this. And then what they've done is they've instantiated this whole workflow in the form of a large JSON config file, which may have slight diffs from customer to customer, but is really just the diffs off of this generalized workflow we've built. They can then basically, because of what we've done, push that into production very easily. So it's at the command line level or GUI level. They're basically saying, I want this now to be in production for this client. And every workflow has its own MD5 hash, so it's completely unique. It's stored in a place that we can go back and roll back to other configs. And then it's no longer the job of the data scientist, once they've pushed that into production, to maintain it, to own it. They will watch our dashboards to make sure that the accuracies as wind up being realized in production are actually what we think they should be. And we set off alarm bells when something doesn't happen, like a prediction hasn't happened over the last hour, when typically we're expecting 10 a second. So some major fail-safes wind up raising alarm bells, but that's more from an operations perspective. So we really just want to make sure that data scientists are part of the building of those templatized data science workflows, and the implementation engineers are the ones that are making those little tweaks. But after that, it's really just an operations problem. And so making that as seamless as possible, that handover, has been where a huge amount of our effort's gone into.
So, and part of your system is built in C++. Part of it is a Python program that consumes the C++. What is the separation of concerns there, and what is the API between the C++ and the Python? And I'm just trying to understand who works with what side of the code. Which, is it data scientists working explicitly with the Python, and you have implementation engineers who are working with the C++? Or I'd just like to know more about that side of things.
Yeah, so one of my co-founders, Damien Eads, is our sort of native C++ guru, and he comes from a really interesting place of having worked in computer vision world where, on a memory and resource constrained environment, you need to work at essentially frame rate. So think about on robots or on drones. You need to make inferences essentially in real time, but you don't have an infinite, supercomputing budget. So you're not going to run TensorFlow, on an ARM chip. So he started approaching some of the machine learning that we needed to do from how do we simultaneously maximize accuracy while minimizing the time to learn or time to predict, and also not blowing up memory. And so it's those three axes on the learning side that are often simultaneously neglected. Many times you'll see people write blog posts about how fast their thing is or how accurate it is, but they won't talk about the third axis. And so at the C++ layer, it allows us to care simultaneously about all those three. Damien and his team have been able to build up essentially our whole learning process. And a big part of that turns out just being very mindful about how you lay data out in memory. If you're smart about it, it means you can very easily move data from disk to RAM through the cache hierarchy and do computation on that in a parallelized way without lots of inefficiencies that come that you might get if you were building in sort of a higher level language. So he's built a large software suite of the C++ layer that allows us to be very, very efficient in learning and prediction. And all of the interesting innovations that have come from the data science team that make its way in the C++ team, are starting at the whiteboard level where we're saying, well, somebody just wrote this paper about how to do this type of machine learning, or use this split criterion in a decision forest. that doesn't quite work for us, but we've got this other idea. They'll whiteboard that out. They'll sort of test it and build out examples of that in Python, and then it'll get pushed into our C++ stack. Then in a new release, we have an API layer that we've created that allows the Python to leverage all the fast and good stuff that comes from C++. And our data science team is then building out those workflows in the Python layer. So it's then the implementation team, which isn't working at C++ or Python. They're working more at the config level, which is making the little tweaks that need to happen to get that specific client into production.
Okay. One of the terms that I've heard you mention when you're talking about machine learning is weak contracts. And a weak contract is an abstraction that bleeds into higher level components or lower level components, depending on how you're looking at it. What is it about machine learning systems that give rise to weak contracts between abstraction levels?
So a good example, and this one came from Leon Bateau in his he gave an ICML talk about this fairly recently, is you have, let's say, a great machine learning model which, given a bunch of images, can make predictions about, let's say, what the most important object is in that image. And I can tell you as somebody who's built this machine learning package that the level of accuracy is this, and the contract I'm going to make with you is that if you give me an image, if I tell you the answer, I'm going to tell you a probability, and that's a well-calibrated probability. So if I tell you there's a shoe in this image with 90% confidence, if I told you that on 10 images with 90% confidence, 9 of those would have a shoe and 1 of those wouldn't have a shoe, right? So that's the contract I'm going to make with you. Now you wind up calling me because you're now building a new app to find shoes and images, because that's how you roll. And you're going to now leverage my black box. And I've guaranteed to you from all the tests that I've ever done that this is what you can expect back. And you better architect your entire system around the fact that I could be wrong 10% of the time. So now you start giving me images, and I start telling you that every image has a shoe in it, or no images have a shoe. And it turns out you're just giving me images of like, a basketball court, or images of different dolphins, right? The weak contract here is that the assumptions that went into building up my explanation of what I'm willing to sign up to are not always made explicit and are not always well understood by other consumers of that part of that stack. And there's some amazing examples of this where if you look at benchmark image classification problems, where you're trying to do over 1,000 class problem, how good is my accuracy? And you do all the right things where you hold out 30% of the data, and then you write your paper saying, I've built this amazing way of getting high accuracy on this multi-class problem, and from my held out testing data that I knew nothing about, I get this level. There's an example, and I don't remember the reference offhand, where you do this just on a class of automobiles or cars, and there's about 7 or 8 papers that claim what their accuracy is. If you then apply that same classifier to other benchmark data sets, also with cars in them, they vastly overestimate their accuracy. So here's an example where it's still just an image classification problem. It's cars. And even though you've done a great job in holding out data, there's something about the fact that the data itself is different, right? Maybe some of these images were taken with cell phone cameras. Others were taken with different aspect ratios by a certain individual at a certain time of day. And all these assumptions about what the data is that went into building the model are completely eroded. And so that's where those weak contracts wind up biting you.
Okay, I understand. So I want to start to close off, conclude by, zooming out and talking about your work in a broader context. You've been involved in several academic domains. You've also been involved in industry, of course. So I'm curious how machine learning is approached differently in academia versus industry.
Well, I'd say broadly, and this is a gross mischaracterization because I'm sure there's counterexamples. Broadly, machine learning is only just making its way into academia and academic research, in part because it's a new tool as viewed by domain scientists, for instance. So if you're a physicist, there are a couple of really interesting problems where machine learning's been around for a while. So, for instance, in particle physics, machine learning has been used, in particular neural nets, for deciding as a new particle is coming through a collider whether you're going to save the data or not. And they've been using this for something like 20 years because they had to. In my own work, we were using machine learning to help us do discovery on massive amounts of images in essentially real time because we realized that we couldn't get enough graduate students to look at the data. Even though my colleagues were telling me just hire more grad students, I knew you had to scale something sublinearly with people. And so obviously machine learning was born out of itself as a discipline. It was born out of computer science and mathematics and statistics. And so it itself had come out of academia, but its use as a tool is only just starting to work its way into the physical domains and more broadly, essentially wherever there's interesting data questions. And I think that's important in some sense because machine learning isn't sort of an end to itself, right? Given all the stuff we've just talked about, this is a big pain in the ass. And so you don't do machine learning, in your work because it's fun. In some sense, you do it because you have to. And there are no other tools that are available to you that are easier to use, frankly, and easier to put in production. And so you're just compelled to have to use it. And so I think what's happening is that machine learning is starting to show up in interesting science domains because it's a useful and viable tool, and the alternatives aren't all that good or don't give as high a level of accuracy. On the business side, I think it's a very similar thing. The companies that have been using machine learning for years are the ones that did it because they realized that was the path they needed to head down to achieve scalability, to achieve high levels of accuracy, to continue to learn on the data as it winds up coming in. And all the innovations that have come in the industry side have come in particular because they've hit the forefront of what other algorithms and other approaches could give them, and innovations needed to happen so that they could get to the next level. So I think in some sense there's different motivations, but ultimately the North Star in both academia and in industry is answering a question. And if that question is how can I make more money, or the question is how can I discover something that no one's seen before, or how can I make better sense of my data in an interesting way, those are all places where machine learning over time may wind up having a really important impact.
Interesting. Well, that sounds like a great place to close off. Josh, I want to thank you for coming on to Software Engineering Daily. It's been really interesting talking to you about Wise.io and machine learning in general. And if you ever have anything to announce or discuss, feel free to come back on the show.
Will do. Thanks so much.